All right, everybody. In this video, I'm going to specifically cover how to use Venn diagrams for standard form categorical syllogisms. And the reason why Venn diagrams are beneficial is they give us sort of a pictorial way of representing both validity and invalidity for standard form categorical syllogisms. So with the counterexample method, which we went over earlier, you can only use counterexamples to prove that arguments are invalid. You can't use counterexamples to show that arguments are valid. Okay. Now, and if you're a little more like pictorial with the way you visualize things or the way you represent things mentally, if you can just look at a categorical syllogism and memorize the rules and say it's valid or invalid, great. But you might not be able to do that. So categorical syllogisms can also be represented with Venn diagrams, where we actually have a visual sort of representation, a pictorial representation of what's going on here. Okay, so I'm going to go ahead and share the marker board here. Okay, all right, so remember when we talked about markings just for how to mark propositions. So if we've got a proposition here between just subject class S and subject class P, we always shade for universals and we always place X's for particulars, okay? So if you need to go back over that with the previous video, feel free to. So if I have a statement of the form all S are P, okay? So that means that every individual member of S is also an individual member of P, okay? Well, if all the S's are P's, that means every single one of them is going to show up here in this middle quadrant, or this middle region, I'm sorry, which means that this region over here is going to be empty. So that is why we would shade this region, okay? All right, so if it's true that every individual S is also an individual P, that means the only place that there can be S's is going to be in this middle region right here, okay? But if all of the S's are here and there can't be any over here, that means that they would also be P's. Why? Because this is the area of overlap or intersection between this S class and this P class, all right? Now, and as I indicated in the previous video, all we are doing with a syllogism is adding another circle, since with a syllogism, instead of 2 terms, we now have 3. Okay, so let's go ahead and label these circles here. So now we have a Venn diagram representing relationships between the minor term, the middle term, and the major term, okay? Now, but since we're adding another term, obviously we have more regions, okay? So now we've got 1, 2, 3, 4, 5, 6, 7 regions on our diagram, okay? Now, so what do all of these regions represent? All right, anything that is here in region 1 is only going to be an M, right? So if you look at the boundaries of this region 1, region 1 does not intersect with the S circle, so this is the boundary of the S circle right here. Region 1 also does not intersect with the boundary of the P circle. So anything that is in region 1 is going to be an M, but it's not going to be an S and it's not going to be a P, okay? Now region 2 is the area where the S circle, one of the areas where the S circle and the M circle overlap, okay? So anything that's in region 2 is both an M and an S, but it's not a P. Now, anything that's in region 3, this is where all 3 of these circles overlap. So anything that's in region 3 is going to be an S and M and a P, all right? Region 4 is where M and P overlap, but not S. So anything in 4 is going to be an M and a P, but not an S, all right? In region 5, this is just S, so there's no overlap with M and there's no overlap with P. So anything in region 5 is an S, but not an M and not a P. Region 6, again, is only where S and P overlap, but not M. So anything in 6 is both S and P, but not an M. And then lastly, anything in region 7 is going to be a P, but it's not going to be an S, and it's not going to be an M. Okay, so here in region 7, anything that's in here doesn't overlap with S, it also doesn't overlap with M. Okay, now if it's helpful, when you're sort of thinking about Venn diagrams and you're dealing with individual categorical propositions and understanding the various relationships, if it's helpful to just focus on the two circles that you're talking about, you know, so let me write a standard form syllogism here. So if I had all P are M, all M are S, therefore I'm gonna have to move this over a little bit. Oh, come on now. There we go. Right. Therefore, all S are P. Okay. So the mood and figure of this would be an A4. Okay. So all P are M, all M are S, therefore all S are P. Right. Now, so if it's helpful, just to look at what you have here. So you're only, with the major premise, you're only focusing on these two circles between P and M. So pretend that this S circle just isn't there. And then likewise, when you're looking at the minor premise, you're only focusing on these two circles. So if it's helpful to just pretend that this P circle is not here when you're dealing with the minor premise, and if it's helpful to just pretend that this S circle isn't here when you're dealing with the major premise, you know, think about it that way. Okay. Now, so if we wanted to mark this, all right, so here with all PRM, so all of the P's are going to be M's. Okay. So that tells me that any areas in the diagram where there could be P's that are not M's, that region is going to be empty. Okay. Now, so anything that's in region 3 and region 4 is going to be both a P and an M, all right? Now, but region 6 and 7, so anything in region 6 is a P, but not an M. Anything in region 7 is a P, but not an M. But since this premise says that all P are M, that tells me that region 6 and 7 are empty. So let's, whoops, supposed to be on draw. Get rid of you. All right, go back to draw. Apparently I can't go back to draw. There we go. Okay, so anything in region 6 and 7 is then going to be empty, right? Region 6 and 7 is empty, so I shade regions 6 and 7 of the diagram. Okay, premise 2 tells me that all of the M's are S's, right? So if all of the M's are S's, that means if any M's exist, they're either going to be in region 2 or region 3. Well, anything in region 1 and region 4 is going to be an M but not an S. But if it's true that all the M's are S's, then that means that region 1 and 4, regions 1 and 4 are likewise going to be empty. Okay. Now, and our conclusion says, therefore, all of the S's are P's. Okay, now, but here, since region 5 is open and region 2 is open, since there are two regions in the diagram where there could be S's that are not P's, that tells me that the argument is invalid. So this is an invalid argument, right? Okay. Let's go ahead and clear this. So I'll just draw a little diagram over here again. Okay, so S, M, P, and I'll try to number these as neatly as I can, although quadrant 3 might, let me try this again. I'm really not good at drawing, especially on a touch screen, so let me be a little more careful here. Okay, that's looking pretty good. All right, Okay, so 1, 2, 3, 4, 5, 6, 7. Okay, and we'll label these S, M, and P. So we've got minor, middle, and major. Okay, now, so just keep this diagram in mind here, and what I'm going to do is write out some rules for constructing categorical syllogism. Okay, rule 1 is this. Only mark premises. Okay, so you do not place markings for the conclusion of the syllogism. You only place markings for the premises. Okay, now here is how Venn diagrams work. If a Venn diagram is valid, then by marking the premises, the markings needed for the conclusion will just show up automatically. So when you mark a premise in a diagram, you're indicating that that premise is true, okay? So keep in mind what it means for an argument to be classically valid. For an argument to be classically valid, it means that true premises will guarantee a true conclusion, okay? So when you place a marking for a premise, you're indicating that that premise is true. So if you place true markings for the premises, and then the marking needed for the conclusion shows up automatically, that indicates that the argument is valid. Now, but if by marking the premises, meaning you're marking that the premises are true in a Venn diagram, if the markings for the conclusion do not show up, that means it's possible for the premises to be true and the conclusion false. And if it's possible for the premises to be true and the conclusion false, that means that the argument is invalid, right? So that's how Venn diagrams correspond to validity and invalidity. So if the argument is valid, then by marking the premises, which means the premises are true, the conclusion should show up automatically. Now, but if when you mark the premises, the conclusion does not show up automatically, that means that true premises do not guarantee a true conclusion. It means that it's possible for the premises to be true and the conclusion false, which means you've got an invalid argument. Okay, so you never, ever, ever place markings for the conclusion. You only place markings for the premises. Okay, so only mark the premises. 2. Universal premises must be marked first. Okay. Now, if both of your premises are universal, it doesn't matter which one you mark first. If both your premises are particular, it does not matter which one of them you mark first. However, if both of your premises are, or if one of your premises is universal and one of your premises is particular, you need to make sure that you mark the universal premises first. Okay. Now, the reason why we do that is you don't want to shade a region on a Venn diagram where you're going to end up, or I'm sorry, you don't want to place an X in a region in a diagram which is going to end up being shaded, right? Because that would be a contradiction. So if you've got a region which is shaded and has an X in it, that means that there's nothing there and that there's something there, which is clearly a contradiction, okay? All right, placing markings, keep in mind that there are 2 regions in play, okay? So if you're talking about M's, you know, let's take a statement like all of the M's are P's, okay? Well, keep in mind in the diagram that there are 2 different regions in play here. So anything which is in region 3 is both M and P. Also, anything which is in region 4 is both M and P. Okay, so it would be a mistake if you're marking all M are P, all the M's are P's. It would be a mistake to only shade region 2 in this case, since we're dealing with all M's are P's. It would be a mistake to only shade region 2 or to only shade region 1. All right, so anything in region 1 is an M but not a P. Anything which is in region 2 is also an M but not a P, okay? But since all M are P means that there aren't going to be any M's which are not P's. That means that region 1 needs to be shaded and region 2 needs to be shaded. You wouldn't only shade region 1 or region 2. You would have to shade both of those regions. Why? Because there's two different regions where there can be M's which are P's. There's two regions where there can be M's which are P's. There are two regions where there can be M's which are not P's, right? Okay, now same with placing an X. So if I give you that some S are M, there's at least one S which is an M, okay, well, there are two regions here where there could be an S which is an M, okay? So anything in region 2 is both S and M. Anything in region 3 is both S and M, okay? So it would be a mistake to just put an X in region 2 or to just put an X in region 3, okay? So that leads us to the fourth rule. If there are two open regions where you can place an X, you place the X on the line separating, spearing, yeah, separating those regions. Okay? So in this example, suppose I give you that some S are M. There's at least one S which is an M, okay? Well, I've got two regions where there could be an S which is an M, right? Anything in region 2 is both an S and an M. Anything in region 3 is both an S and an M. Okay, well, what if I place my X in region 2? What if I place my X here? Okay, well, what am I saying? If I place an X in region 2, that means I'm saying it's S and an M, but not a P, right? Now, unless I've got some premise which indicates that there's at least one M which is not a P, or I'm sorry, that no M's are P's or something like that, I'd be saying more than what's actually given to me in the premises. So if all I have are some SRM and I place the X in region 2, I'm saying that it's an S and an M, but it's not a P. So I'm actually saying more than what's given to me in the premises. Likewise, if I put it in region 3, I'm saying it's S, M, and P. But if all I'm marking is there's at least one S which is an M, I don't know if it's a P or not a P. Since we don't want to say more than what's actually given to us in the premises, I would have to put my X on the line separating those two quadrants. So that tells me that I know there is an S here, which is also an M. So it's somewhere either in quadrant 2 or quadrant 3. But since I don't know whether it's in quadrant 1 or quadrant 3, I place the X on the line separating quadrants 2 and 3. Okay. Now let's go back here for a moment. Whoops. All right. Screwed this up, so I got to move this right there. Okay. Rule number 5 is the no dangling X's here. Okay, so you're not gonna place the X on the intersection of two lines, and you're not gonna place an X in a way so that they're actually dangling outside of a diagram. Okay, so you're never gonna place an X here, right? So there's at least one X, but I don't know if it's an M or a not M. Well, it's got to be one or the other. So there's something here, but it's either an M or it's not an M. You're never going to have a premise which says there's at least one thing which is either an M or it's a not M. That's what this says. There's at least one thing which is either an M or it's not an M. That doesn't make any sense. Okay. You would never place an X here. You would never place an X here. Never place an X here. Never place an X here. Never place an X here, or never place an X here. Okay, so you can place an X on a line that separates two quadrants, but you would never place an X on the intersection of two lines, or you're never going to place an X in a way so that it dangles outside of a diagram. You're actually not communicating anything by doing that, right? Okay, so let's go over a couple of examples here, right? So let's do a EIO2. Okay, so if we wrote this out in standard form, that would be no P are M, some S are M, whoops. Therefore, some S are not P. So we've got an EIO. So the major premise is an E and it's in figure 2. So the middle term comes second in both premises, no PRM, some SRM, I, therefore some S are not P, O. Okay. Now, if we were to mark this with a diagram, here's what it would look like. Okay, label our circles here, S, M, and P. All right. Now, if it's helpful, I'll go ahead and write in the numbers. 1, 2, 3, 4, 5, 6, 7. Okay. Now, so remember the rules. We only mark the premises. So we're going to mark this statement, no PRM. We're going to mark this statement, some SRM. All right. And if the syllogism is valid, the marking needed for this conclusion to be true is going to show up automatically. Okay. So in order for this conclusion to be true, there's either going to be an X in quadrant 5, or there is going to be an X in quadrant 2, right? So if there's an X in quadrant 5, that means, or in region 5, that means that there is something here which is an S, but not a P, right? Since that's the boundary of the P circle. Now, likewise, anything that appears in quadrant 2 is going to be an S and an M, but not a P. So if we get an X here, this statement is true. Likewise, if we get an X here, this statement is true. So that is the marking, or there's at least 2 markings here that we're going to be looking for. Okay, get rid of those X's. Okay, so no PRM, right? Now, so that means if the M class and the P class are excluded from each other, that means any area of overlap between them is going to be empty. So none of the P's are M's. Likewise, it would follow that none of the M's are P's, right? So if these 2 classes are excluded from each other, that means any area where they intersect is going to be empty. So that means we would shade regions 3 and 4. So since regions 3 and 4 are shaded, I know that there aren't going to be any P's which are M's. Why? Because these 2 quadrants, regions 3 and 4, are empty. Okay. Now, premise 2 says there's at least one S which is an M. Okay. So there's at least one thing which is an S and an M. Okay. Now, but since I know that region 3 or quadrant 3 is empty, the only place that I can put an X is here in region 2. Okay, so anything in region 2 is both S and M. Anything in region 3 is both S and M. But since region 3 is empty, why? Because no P's are M's, which means that region 3 has to be empty. The only place I can put my X is in region 2. Okay, now, but remember what we said. If I have an X in region 2, that means that there's at least one S, which is not a P, right? So if you look at this boundary, this is the P circle. So there's an X here, which means there's something here. So it's both an S and an M, but it's not a P. So by marking these 2 statements as true, so this one is true, this one is true. So if these 2 are true, it means that this one is true as indicated by the diagram. Okay, so what does that tell us? This tells us that this argument is valid. Okay, that's how Venn diagrams work. So I placed markings for the 2 premises, and by marking the premises, the conclusion showed up. There's at least one thing here, which is both an S and an M, but not a P. So there's at least one S, which is not a P. Okay, that's the marking I need. That's a marking I need for the conclusion to be true. So 2 true premises guarantee a true conclusion. If both of these premises are true, the truth of the conclusion is guaranteed, as indicated by the diagram. So this is a valid argument, right? Okay. Now let's do another one here. So let's do an III. Okay, so what would that be? So all my premises are I statements. So whoops, some M are P, some M are S, therefore some S are P. Okay, let's draw the diagram here. Okay, S, M, and P, minor, middle, and major. Let's number them. 1, 2, 3, 4, 5, 6, 7. There we go. Okay, so I don't have a universal premise and a particular premise. I have two particular premises, so it doesn't matter which one I mark first, but let's just go ahead and go in order here. All right, so the major premise says there's at least one M, which is also a P. So there's at least one thing somewhere in here, okay? Now, but remember, anything in quadrant 3 is both an M and a P, but it's also an S. But does this say some M, R, P, and S? No, it doesn't say that, okay? So if I put this X in quadrant 3, I'm gonna be saying more than what I'm actually given in the premise here. I'm not told there's at least one thing which is an M and a P and an S. Nope, I'm not told that. So if I put this X in quadrant or in region 3, quadrant 3, region 3, whatever, I'm actually saying more than what's given to me in that major premise. Now, likewise, if I put that X in quadrant 4, I'm saying it's an M and a P, but not an S. So I'd be saying more than what I'm given in this major premise, okay? So since I know there's an M here, which is also a P, but I don't know if it goes in region 3 or region 4, I need to put my X on the line separating those two regions. So I know there's an M here, which is also a P, but I don't know if it's also an S or if it's not an S. I'm not told, right? So I'm ignorant, right? Okay. Now, this says there's at least one M which is an S. Okay? Now, and this can be a common error thinking about this. So keep in mind what the word some means. The word some just means there is at least one. So there's at least one M which is a P. There's at least one M which is an S. So you may be thinking, okay, well, wait a minute. You said we couldn't put an X here because I don't know if something is an M, a P, and an S, but this says there's an M which is an S. So can't we just like move this S up here? No, we can't, and here's why. Okay, so if I'm saying there's at least one M which is a P, and there's at least one M which is an S, does that necessarily mean I'm talking about the same object? So there's at least one animal which is a cat. There's at least one animal which is a dog. Both of those statements are true, but clearly, you know, the M I'm talking about here is not necessarily the same M that I'm talking about here, right? So even though I've got a premise here that says there's at least one M which is an S, I don't get to let that condition the marking that I put for this premise up here, because I could be talking about two completely different M's in between these two premises. So there's at least one animal which is a cat. True. There's at least one animal which is a dog. Also true. So clearly I'm not talking about the same animal anytime I say there is at least one. So I don't get to assume that the M I'm talking about here is the same M that I'm talking about here. That doesn't follow. Okay, Now, but since this just says there is at least one M, which is also an S, okay, well, anything in region 2 is both M and S. Likewise, anything in region 3 is both M and S. So if I put my X in region 2, I'm saying it's an M, it's an S, but it's not a P. But there's nothing in this premise which says whether it's a P or not. Likewise, if I put it in region 3, I'm saying it's an M, it's an S, and it's a P. But I'd be saying more than what I'm actually given in the premises. So for premise 2, the minor premise, there's at least one M, which is an S. I would put my X again on the line separating those two regions. Okay, so what's my conclusion? Therefore, there is at least one S, which is a P. Okay, well, what would give me that? If there's an X in region 6, I know there's an S, which is a P. If there's an X in region 3, again, I know there is an S, which is a P. But since I don't have an X either in region 6 or in region 3, I don't have the markings needed for the conclusion just by marking the premises, right? So by marking the conclusion, or I'm sorry, by marking the premises are true, as true, the marking needed for the conclusion does not show up. So it's possible for the premises to be true and the conclusion false. So this means that this argument is invalid. This is an invalid argument. Now, and bear in mind, you could also do this with a counterexample. So there's at least one M, which is a P. There's at least one animal, which is a cat. There's at least one animal, which is a dog. Therefore, there's at least one dog, which is a cat. True premises, false conclusion. This is an invalid argument. Okay. All right, let's do one more here. Let's try an EAO. Let's do an EAO1. Okay, so what would that be? Right. No M or P, all S are M. Therefore, some S are not P. So no M or P, and all S are M. Therefore, some S are not P. Okay. Diagram. Okay, go ahead and number these. 1, 2, 3, 4, 5, 6, 7. There we go. Okay, now, once again, both my premises are universal, so it doesn't matter which one I place markings for first. So let's just go in order here. All right, so no M or P. So that tells me that these two regions, regions 3 and 4, are empty, right? So since 3 and 4 are the two regions where there could be M's, which are P's, that means that these two things need to be shaded, since no M's are P's. Okay. Premise 2, the minor premise, all of the S's are M's, right? So if all of the S's are M's, that means any regions where there could be S's that are not M's are also going to be empty, okay? So since region 2 is the region where S and M overlap, since region 3 is empty, okay? If there are any S's, they're going to be here in region 2, right? Now, but anything in region 5 is an S but not an M. Anything in region 6 is an S but not an M, okay? But if all of the S's are M's, this tells me that regions 5 and 6 are going to be empty, okay? All right, and our conclusion, therefore, there is at least one S, which is not a P. Okay, well, my conclusion is particular. And what's the marking for a particular conclusion? The marking for a particular conclusion is an X. But I don't have any X's in my Venn diagram, right? I have no X's here. Now, the only place where there could be an X, which would make this conclusion true, there's at least one S which is not a P, is here in region 2. Now, but since I don't have any X's in region 2, why? Because I don't have any X's at all in my diagram, right? This tells me that this is invalid, right? So this is an example of, the breaking rule 5. You can't have universal premises and a particular conclusion. This is the existential fallacy, okay? Now, so if we were working in Aristotelian logic, okay, I would have to look at whether or not S refers to an actually existing thing, okay? So if this were my argument, suppose, let me rewrite this. Right? No dogs are cats. All poodles are dogs. Therefore, some poodles are not, are not cats, cates. All right. So no dogs are cats. All poodles are dogs. Therefore, some poodles are not cats. Okay. Well, S here is what's called a critical term. So what's a critical term? So a critical term in traditional logic is a term that is actually being distributed when it doesn't have to be distributed, okay? So S is being distributed in the minor premise, but it's not being distributed in the conclusion, which means that this would be a critical term, okay? Now, and since the critical term, since the critical term is poodles, is there at least one poodle? Do poodles exist? Yes, they do. Okay, well, since my critical term refers to an actually existing thing, I can empirically verify that there's at least one poodle. I can place an X in this circle, in this region, sorry. I can place an X in region 2 and actually put a circle around it. And when you put the circle around the X, that means, that indicates that you're interpreting a universal premise as having existential import. Okay, so in a situation where you're dealing with traditional logic, where you're dealing with Aristotelian logic, where universal statements do have existential import, this is how you would account for that in a Venn diagram. Okay, now, but we're not going to be doing that. So for our purposes, we're only using the modern or the Boolean interpretation of logic, where we're treating universal statements as if they don't have existential import. Okay. Now, but in this situation where in traditional logic, where you're trying to determine whether a critical term, actually refers to something, you would need to look at what the critical term actually is. In this case, the critical term is poodles. So the minor term is the term which is being distributed when it doesn't have to be. That makes it a critical term. So this argument is conditionally valid on the existence of poodles, but since we know that poodles exist in traditional logic, this would be valid, okay? Now, but this is always invalid in modern logic. In modern logic, this commits the existential fallacy. We're going from universal premises to a particular conclusion. You can't do that in modern logic. You can do that in traditional Aristotelian logic, okay? All right. Okay, that will suffice for now. Again, I know Venn diagrams can be a little bit confusing, but I hope this video helps clarify a few things. And as always, if you have any questions, do not hesitate to email me. I'll see you all later.